All right, everyone. This is Kristlyn Partica, the project manager for the Northern Grapes project. I'm really happy to see that we have so many people signed in and ready to go. It looks like it's noon, so I'm going to go ahead and change the screen a little bit so that we can get started with Tim's talk after I finish the introductions. So our first speaker today is Dr. Tim Martinson from Cornell University, who's the project director for the Northern Grapes project. He's going to be giving us a brief overview of the project and of the webinar series as a whole. After that, we'll have Dr. Murli Dharmadhikari from Iowa State University and Dr. Katharine Mansfield from Cornell University, who will be giving us a great talk on how to manage acidity in the winery. Their talk is going to be split into two sections, and we'll have a short break for some questions in the middle. And remember that as a participant in today's webinar, you will not have the ability to speak. If you are having technical difficulties, please type a note in the chat pod over on the left side of the screen, and I'm going to do what I can to help. If you have any questions, please type them in that same chat pod on the left side of the screen. Chris Gerling, who is an Enology Extension Associate with Cornell, is on hand today, and he's going to answer less detailed questions in that same chat pod as the presentation progresses. More involved questions will be collected, and Murli and Katharine will answer as many as time allows during the break, halfway through the presentation, and again at the end. And we're going to keep a list of any questions that aren't answered during today's webinar, and we'll post them on the web shortly. And I will send out a URL with that address at some point, I promise. So let's get going, and I'm going to turn things over to Tim to give a brief overview of the project.
Hi, good morning, everybody. I hope you can all hear me well. I'd like to, my name is Tim Martinson. I'm the Senior Extension Associate with Cornell University, and I run the statewide viticulture extension program. I'm also a project director for the Northern Grapes project, which came about based on a discussion I had with Murli many years ago at the Unified Symposium, asking, these Northern Grapes have made grape production possible in places where we've never had grapes before. I wonder what the return on investment has been for University of Minnesota program and of course the private breeders. So that was the start of our project. We're very gratified by the response we got, and you can see here I'd like to welcome everybody from Wisconsin to New Hampshire, Oklahoma, and places in between. Thank you for signing up for this. This is a brand new thing for me. This is the first webinar I've ever hosted or tried to do, and I hope that this will be a useful method of providing some information and feedback. I'd like to emphasize that we'd like this to be participatory, so please feel free to type in comments at any time, questions in the chat box. I'd like to welcome some groups, some people that are hosting groups. I believe Katie Cook is hosting one in Minnesota, and Tim Rabin down there in Vernon County in Wisconsin. We think this is a great way to have a group there and be able to have some follow-up discussion or whatever. With that said, I'd like to welcome you again to the webinar, and going to spend just a few minutes here describing what the Northern Grapes project is. This is a 5-year project that's funded by the United States Department of Agriculture Specialty Crops Research Initiative. It came about because we had some planning sessions in Vermont and Minnesota several years ago that some of you were at, and we're able to, based on the input we got from people all over the northern Midwest and New England about what sorts of projects you'd like to have. We were lucky to get it funded for $2.5 million for the first 2 years. As I mentioned, it's slated to be a 5-year project. But part of the deal with this grant program is that we have partners, and they've provided a one-to-one match, and that includes universities and grower cooperators and so forth, and other groups that have provided matching funds for this. So really that $2.5 million represents a total investment of $5 million if you count in all the matching funds. The project team is 30 research and extension team members from 12 different institutions. We have expertise in viticulture, enology, and economics and marketing. We have several teams that are working together. And also we've, in the course of writing this and doing the project, we've signed up with 20 cooperating winery and growers associations in your local states. So what's a simple way to describe what we're after? Well, it follows from this very simple logic model in which in which you start out with the viticulture, and of course it's important to grow quality grapes, and the grapes go into winemaking. So basically looking at the enology and what we can do to produce high quality wines that consumers want. Of course, making good wines is only the second step, and the final step there is selling them. So the third aspect of the project focuses on consumers and understanding marketing, sales, and promotion for these new wines made out of the new varieties in new places. And we hope that by focusing on these 3 areas broadly, that will equal a focus on making a profitable, vibrant industry and planning for the future. Just briefly, I want to go over 4 basic areas in which we're going to be doing research projects. The first area focuses on the vines themselves. These were released quite recently. I believe the first Minnesota variety came out in 1996, and of course the Swenson varieties have been around for a little longer, and then there's some newer ones. But our first goal is to really do studies to test varietal performance and the wine flavors, attributes that result in different climates. The second focus will be on vineyard management. That is, we want to find out how to apply appropriate practices so that we can achieve consistent fruit characteristics for winemaking. And I might mention here that it's easy to produce good wines in good years, but we have the cooler than average years that might be a little bit more of a challenge. So we think that adapting viticulture practices for the climate will help out with that. Winemaking, of course, these varieties are things that have some unique characteristics from a winemaking perspective, which we're going to address today. So we're going to be looking at different winemaking practices that will allow you to produce distinctive high-quality wines that are going to be valued by consumers. The fourth area is consumers and marketing, and since many of us, myself included, are new at this, we want to focus on understanding consumers and strategies on an individual and regional basis that can increase sales and growth of wines made from cold climate cultivars. Okay, that's it in a nutshell. And we have several different outreach things. These Northern Grape webinars are something that we hope to do on a monthly basis and continue on, and will be one method. We also have a symposia that our first one will be at the Minnesota Grape Growers Convention on February 23rd. So winter meetings, the newsletter, we hope to put out a quarterly newsletter that will include project updates and inform you all about the project in general. Then we'll have some detailed workshops and field days through the summer. And finally, at the end of the 5-year project, we hope to come out with what we're going to call the Northern Grapes Owner's Manual, which will be production guides and so forth. These webinars, basically, they're monthly. We hope they will be interactive, so please feel free to provide any sort of feedback in the chat lines or elsewhere. We decided to make this a topic-based series. In other words, it's not going to be a course where we have follow through in a logical area. We're going to jump around and have topics based on winemaking, viticulture, and then marketing. So your participation is important in this, so I encourage you to ask questions through the chat pod. We will have at the end of this a exit survey, which we'll place on towards the end of the talks with a URL where you can provide us with feedback and suggest topics. The other thing I wanted to try out this time is, I don't know how many of you know about Twitter or on Twitter. I'm not a big Twitter user, but I've come up with this hash mark #NorGrape that you can type into messages and send out, and then we can search through things with that tagline later on. If you'd like to ask questions through Twitter, that would be great. And finally, this will be recorded, and announcements about the series will be posted at the web address you see below. Okay, just briefly, our first Northern Grapes Symposium is going to be on February 23rd in St. Paul, entitled From Vine to Cash Register, What the Northern Grapes Project Will Do to Help Develop the Cold Climate Grape and Wine Industry. So that will be in St. Paul, and I hope to see many of you there and at the conference. Finally, our next webinar will occur on February 14th. That's the second Tuesday of February. And that will be me and Mike White discussing the nuts and bolts of canopy management. We will be sending out an announcement and the registration information approximately 2 weeks before that, the end of January, early in February. So look for that if you want to sign up for the next webinar. And with that, I'd like to turn it over to Murli and Katharine, who will be talking about managing acidity in the winery. Murli?
Good morning and hello everybody. This is Murli Dharmadhikari from Iowa State. I'm Extension Enology Specialist for the state of Iowa, and I'm kind of tickled pink to be able to present this seminar or webinar this morning or afternoon, depending on what time you have. So let's get started with the, first we'll try to cover some of the basic aspects, and then we'll talk about the treatments later on. So to get us started, let's first look at the sources of organic acids in the wine. And the first source is obviously grapes, because we are talking about making wine from the grapes, from the cold climate region. The organic acids contributed by the grapes include tartaric, malic, and citric acid. And of the three acids, tartaric and malic constitute about 90% of the acid content. The second source of organic acids in wine is the fermentation. Both alcoholic and malolactic fermentation will contribute to some acids. These acids, fermentation acids, include succinic and lactic acid. And the succinic, lactics plus grape acids together, these 5 acids constitute fixed acidity because they are not volatile. The acid that is produced during fermentation that is volatile is called acetic acid, and this acetic acid constitutes volatile acidity, and it has an impact on both the odor of the wine as well as the taste of the wine. The fixed acidity and volatile acidity together constitutes total acidity, which is usually measured by the analytical means like HPLC, and that really measures the total acid and ions. And another way acidity is expressed is titratable acidity, which measures some percentage of total acidity. So don't confuse between these two terms. Generally, titratable acidity is about 70% of total acidity. Okay, moving along, looking at some of the major acids. To begin with, tartaric acid. This is a dicarboxylic acid, which is principally present in grapes. It's rare in other fruits, but it does occur in grapes. And the concentration varies depending upon the variety, but generally it's in the range of 5 to 10 grams per liter. And most of this literature is for vinifera grape, but even in some of the Rapira hybrids, Riparia hybrids, the concentrations can be significant. The tartaric acid accumulates during the pre-veraison, or the first stage of berry growth, which starts after the fruit set and somewhere just before the fruit begins to change color. So that's the stage where this acid accumulates. And the important point to remember is this acid is stable in wine. That means it is not degraded by yeast or lactic acid bacteria and stays in wine. The second acid is the malic acid, which is also a dicarboxylic acid. And generally it is present in a lesser amount than tartaric acid. The range is somewhere 2 to 4 grams per liter. But in our cold climate grapes, it can be higher, something like 8 grams per liter or higher. And this is predominantly a major acid in cold climate grapes that gives us a few headaches of high acidity and high pH. The concentration of malic acid also depends on cultivar, but it's important to realize that the concentration is also very sensitive to the temperature during the growing season. For example, in warmer climate, there is a greater reduction of malic acid and less malic acid is present in the grapes at harvest. The malic acid is also vulnerable to microbial action, and both the yeast that conduct alcoholic fermentation as well as the lactic acid bacteria that conduct malolactic fermentation can degrade malic acid. So this is not a very stable acid, and the concentration will vary. So let's spend a minute on the sensory characteristics of these acids. As you are very familiar with the acid taste of the wine, if the wine has very high levels of acid, the wine will taste tart, thin, and very green. On the other hand, if the acid is low, then the wine tastes pretty flat and flabby and out of balance. So even though we have 3 acids present, their perception varies somewhat. And if you look at this chart that shows, or diagram that shows from most acidic to least acidic, tartaric is the most acidic, and malic is in between, where lactic is the least acidic. All the 3 acids have the impact on the taste of the wine and do not contribute to the volatile aroma that is contributed by the acid, which is called acetic acid or vinegar. Now I would like to draw your attention to acidity measures, and particularly the topic of wine pH. pH by definition is a negative log of the molar concentration of dissolved hydrominium ions. That's pretty mouthful. Basically it's a concept. It's nothing tangible like acids or sugar, but it is a concept that simply tells you the acidic or basic properties of the solution. The pH scale is between 0 and 14, 7 being neutral, and the solutions with pH values of less than 7 is considered acidic, and the solution with pH values greater than 7 is considered basic, and 7 being the neutral. There are a couple of other important aspects of pH that we need to know. For example, the acidity of the juice in wine is somewhere between 3 and 4, and therefore it is considered a mildly acidic solution. There are 2 important aspects of wine pH that I would like to point out. First of all, it's a logarithmic scale. that means the difference between pH unit is tenfold. And second thing is it's a negative scale. That means the lower pH value indicates higher hydrogen ion concentration and therefore higher acidity. So it's like backward, but once you get the hang of it, it's not that bad. I would also like you to consider that wine pH is very important to the winemaker because it affects several things, aspects of winemaking. The first is it influences the chemical reactions such as oxidation, browning, ester hydrolysis. All these chemical reactions are influenced by wine pH. It also affects the physical properties such as stability of heat unstable proteins or precipitation of bitartrate. These things are influenced by pH as well. And we all are aware of the fact that pH also influences microbial stability of both juice and wine, and especially higher pH values tend to favor spoilage, causing wine microorganisms to flourish, and therefore we should pay special attention to high pH and protect the wine. The pH of the wine depends on many factors, but to give you some idea, so these factors would include fruit maturity, cultivar, crop levels, season, soil moisture, mineral composition, and amino acid concentration. But the most important thing is that it is the strength of the acid, and the greater amount of tartaric acid, the lower the pH is going to be. And the second most important factor that influences wine pH would be the concentration of potassium. And what we find in cold climate grapes is the concentration of potassium is very high, and that leads to high pH value. So as a winemaker, what pH you should be looking for? So if you look at from very acidic to high pH wine, somewhere in the range of 2.8 to 4.0, if you have a pH much higher towards 3.8, you will have an increased risk of microbial growth. Around 3.7 is still high pH. It will have impact on palate. The wine will taste flabby and flat, and if it's a red wine, the color would be somewhat dull. So ideally what you are looking for is the pH around 3.3, give plus or minus 0.2 units, because that's really desirable pH, because it helps you take care of the wine very well. You use less sulfur dioxide with the low pH, and it's more effective, giving you protection from both microbial spoilage and oxidation. And the wine tastes a little more balanced, and it's much more fresher on the palate. So that's the effect of pH on wine. Now, I would like to invite Dr. Katharine to continue this discussion and talk about acidity measures, and especially titratable acidity. So, welcome.
Great, thanks, Murli. And I'd like to remind everyone, if any questions come up as we're talking about these slides, to please type them in the chat so that Chris can have them ready for us when we have question and answer session after this first part of the talk. So Murli talked about pH, which is one of the two acidity measures that are important to us as winemakers. And the second one that is equally important is titratable acidity, which we generally abbreviate as TA. And TA is the measure of the number of protons that are neutralized by a strong base. And we measure this by titrating to an endpoint of 8.2, which is kind of an arbitrary number, but is used because it happens to be the number where phenolphthalein changes color. So if you need to measure your TA without having a pH meter around, it's a nice visual way to note that color change and know when your titration is over. So as Murli mentioned before, we do want to stress that titratable acidity is always less than the sum of your organic acids present, because you're never able to titrate and therefore measure all of the acid in a juice or wine sample. But sort of as a shorthand, if we consider pH to be the strength of the acid that we have in our wine, you can kind of, again, in a roundabout way, think of TA as the amount of acid that you have. So rule of thumb, pH is strength of acid and TA is the amount of acid, and they're both important. We'll explain why in a second. So to give you a sort of an overall visual idea of where TAs can run, if we are looking at very warm climate cultivars grown in warmer regions, we can have TAs as low as 4 grams per liter of acidity. In cooler regions, say that the Finger Lakes, where I'm sitting right now, looking out on a gray day, we could get TAs more between 7 and 9 grams per liter. That's going to give you a more bracing acidity, more palate structure. But when we're dealing with the Riparia-based hybrids from cold climates, we can see TAs as high as 16 grams per liter, and really worst case scenarios, I've seen them as high as 22 grams per liter, which is a bear to work with, certainly. That can range a bit, can be as low as 12, but we're definitely seeing numbers that are a little bit higher than we're used to in Vitis vinifera. Another thing that's important to remember when you're measuring your titratable acidity is that we talk about our total titratable acidity, and it's sort of in a shorthand. We assume that all of the acid in the wine is tartaric acid, and that's just for convenience. We really are measuring all of the acids in the wine, but we express them as if they were all tartaric acid equivalents. That's why you run that long, complicated calculation at the end of your titration. It's important to remember, if you are reading older textbooks on wine, discussing wine with colleagues in France, or discussing with your colleagues in Quebec, that there are other ways of expressing the same number. And in France and Quebec, instead of deciding that we're going to assume everything is the most common acid in the wine, they've decided to use an acid that isn't in wine at all and convert everything into sulfuric acid units. So if you look along the top row here, you see that an equivalent amount of acid in tartaric units is quite different than in sulfuric units. So we have run into some confusion from time to time when having cross-cultural discussions. Important to remember. So now that we know what pH and TA are, let's look at some of the situations that we may cover in wine. And the first is one that is not so typical to our regions. If we have a high pH and a low TA, so low acid, that's tracking pretty well, because if you remember, as acid gets higher, pH will get lower, or and vice versa. In this case, which we tend to see in warm climates like California, if the wine is balanced, you can leave it alone. If it is not balanced and you need to do something to keep it from being too flabby, we acidify the wine. Again, not something that we tend to see in most of our growing regions. The flip side of that would be having a low pH and a high TA, and again, this makes sense chemically. It tracks pretty well. Our acid's going up, pH is going down. If it's balanced, to leave it alone, you should be good to go. If you need to drop that acid a little bit, then you can still deacidify pretty comfortably, because you aren't going to cause your pH to do anything too strange as you adjust the TA. It should track nicely. Now, where we run into problems is when we see a situation like this, where we have a high pH and also have a high TA. And this is a case where our pH isn't tracking with our acid, and if we try to get in here and deacidify, we run the risk of pushing that pH up even higher. If it's already at, say, 3.5 and you are going up a few units above that, you can find yourself in the range where microbial contamination is a problem, and where you also may have issues with sensory. So in this case, we need to deacidify or protect the pH. The converse of this situation is where you have a pH that is low and a TA that is low, and fortunately for us, this does not happen on planet Earth, so hopefully we don't see this problem. If you do see this problem, that means you probably need to either check your pH meter or look at the reagents for your titratable acidity, because something isn't adding up. So there's some other complications, unfortunately, when we're dealing with wine, and that is the fact that there's no good correlation between pH and TA. Because wine is a pretty complex matrix, there's a whole lot of stuff going on in there, we can't measure one or the other and predict the second value. And in order to illustrate why that's an issue, I've got a hypothetical situation here. Let's assume that we're looking at wines that all are at the same titratable acidity. We'll just call it X grams per liter for now. If we had a wine, hypothetically, that was 100% tartaric acid, which never happens in the real world, but no malic at all, no succinic, anything else, at a given TA, our pH would be relatively low. Because while tartaric acid is an organic acid, and therefore a weak acid, it's a fairly strong, weak organic acid, so a high TA will generally give us a low pH. Now, in a second hypothetical situation, if we had a wine at the same titratable acidity that was composed entirely of malic acid, we would have a relatively higher pH because malic acid is not as strong as tartaric. Of course, neither of these happen in the real world, but just to give you an idea of what's going on, those are our options. Now, if we took the same hypothetical 100% malic acid wine and we fermented it with malactic fermentation and ended up with lactic acid, we would see a lower titratable acidity, which we could adjust by then adding back some tartaric acid. And what we'll get is actually a fairly moderate pH. So because lactic acid is very weak, tartaric acid is a little bit stronger, you can actually adjust the pH down to something that is a little bit better than having lots of malic acid. So you can see that the acids themselves cause some differences. So when we end up with the mixture that we have in wine, it gets very complicated, but the relative amounts of tartaric or malic acid can affect that pH. So just measuring your TA doesn't always give you an idea of what your pH should be. Another thing that complicates things is the fact that we have potassium in our wine, which is the symbol for potassium is the K. That's why that's up there. And potassium is an important macronutrient. It generally increases during ripening, and it's affected quite a bit by soil type, growing conditions, cultivar, viticultural treatments. I believe my colleagues at the U of M are looking at the effects of some viticultural treatments on potassium content. But the reason we care about it when it gets into the wine is that, of course, it's in the grape, so it's in our juice, and potassium tends to nudge our pH higher without affecting our TA a lot. So a lot of potassium can sometimes lead to a situation where we have high pH and high TA, and that doesn't give us a lot of wiggle room to correct it. And we'll talk about why in the next section. So that's another thing to be cognizant of. It's not particularly easy to measure potassium in a small winery situation. So it's something that's hard to detect sometimes. So because we have all of this going on in the wine, the potassium, all of these different acids, wine is what's called a buffer solution. It has buffering capacity. And what that means in real-world terms is that additions of acids or bases cause only small changes in the pH. Because of this, it's easier to change our TA than to change our pH. That's something we have to keep in mind when we are trying to adjust our wines at the end of the fermentation process. And also the reason why if you're doing your titrations, you find sometimes that you're making small drop-wise additions, everything's looking good, you're not getting huge color changes, and then all of a sudden it overshoots and you've got this horrible pink color like you see in the lower right-hand corner of the slide. That's why, because the wine with the buffering capacity is sucking up all of these ions that you're adding, and then all of a sudden it's reached capacity and it overshoots. So you can blame buffering capacity on that problem as well. So when we talk about acids in wine, our goals are to balance the sweetness of the wine, and on the sweetness side of the equation we also think about fruitiness and viscosity, with acidity, or in the case of red wines, also astringency and bitterness. So we want a TA that's low enough to provide flavor balance, but a pH that's also low enough to protect against microbial pests. So at times these can be at odds with one another. In the traditional literature, there are some recommendations for this, for Vitis vinifera at least, and I have to give credit to Katie Cook at Minnesota for giving me this data. The recommendations traditionally from 100 years ago are that the tartaric and malic ratio should be about 1.2 or less, greater than 1.2, and that our malic acid content should be less than 60% of the measured TA. So again, we haven't determined this experimentally in our cold climate cultivars, but it is certainly a starting point and worth considering. So in cold climates, our challenges are that we tend to have high TA, often in excess of 12 grams per liter, sometimes as high as 16 or 18. High malic acid in some regions, and this varies quite a bit. I know Murli has seen some of this in Iowa. We didn't see it as often in Minnesota, so it may vary by macro climate. And high potassium, which can really vary by site. We have seen areas where one farm will have high potassium issues in their grapes and the next farm over won't. So that is quite variable and hard to predict. So our question is, how can we lower acid without raising pH to an unacceptable level? And I believe that is the end of our first portion of our talk, which is our introduction to the basics. Kristlyn now will hop on and we'll have some question and answers, and then Murli and I will continue with the second part of our talk.
All right, everyone. We actually haven't gotten any questions yet. If anyone has them, type them in now, please, and we'll answer them. I think I will mute my microphone again because I don't have much other to say than that.
So I see that Kurt has asked a question. How do we know when the malic is greater than 60% of the TA, the titratable acidity? And no, Kurt, you didn't miss that. That actually is something that is a little bit more complicated to measure. In a small winery situation or a home lab, you can certainly measure your TA, all its titratable, by running a titration. In order to measure individual acids, you've got to have more complicated equipment. So either some high-performance liquid chromatography, or HPLC, which is what we would use in a wine lab to measure individual acids, or there are some enzymatic test kits that you can use if you have a spectrophotometer. So it's not something that a small operation can do very well. So I only mention that in case you notice over time that you continue to have TAs and your pHs are not matching up with the TAs you're seeing, you know, very high TA, but the pHs aren't as low as you think they should be. If that's a problem year after year, it might be a good idea to indicate, or excuse me, to contact your extension agent or go to a professional lab and see if you can have your malic tested and also your potassium, and that might start to give you some clues to why you're having issues. Keith, Keith wants to know if we can state TA in percent instead of grams per liter. Grams per liter is the accepted way. It's really just move the decimal point over 1. So if I'm saying 10 grams per liter, you're looking at, you know, 0.1. So 1.
Okay, we are going to keep the list of these questions, and we can either address them at the end or they'll be answered and posted online somewhere. So why don't we go ahead and have Murli pick back up with the second part of the talk now.
Okay, that sounds good. Let's begin our second portion of this presentation, and we'll discuss some of the treatments for reducing the acidity in wine. The first option that I would like to talk about today is the biological deacidification, which would involve the use of both the lactic acid bacteria as well as yeast strains that are involved in alcoholic fermentation. So the first, let's look at the malolactic fermentation, which is conducted by lactic acid bacteria. This is a very simple conversion of malic acid to lactic acid with carbon dioxide being evolved. Notice that a 2-carboxylic acid, which is malic, is being converted to 1-carboxylic acid function, and therefore there will be a reduction in titratable acidity, and consequently there will be an increase in wine pH. However, there is no problem that it is very difficult to predict the changes in TA and pH after malolactic fermentation. And the reason for that is, for example, yeast will degrade the malic acid and make ethanol as opposed to lactic acid, which is produced by lactic acid bacteria. So that has different impact on acid as well as pH. The second thing is that lactic acid bacteria can convert sugar to lactic acid. So if you are just looking at expecting a certain amount of lactic acid to be formed from malic acid, you could be surprised because some of the sugar is also being converted into lactic acid. So the titratable acidity could be a little more than what you expect. So for this reason, it's very difficult to predict the changes in TA and pH. The third point that can complicate the factor has to do with the precipitation of potassium bitartrate. When that happens, you'll have impact on both pH and TA. TA will decrease, and pH will either decrease or increase depending upon your beginning pH of the wine. So assuming that you want to conduct malolactic fermentation, your next question is going to be, what's the best time to inoculate the wine to initiate malolactic fermentation? You have several options, and I have listed here three. The first one is at the very beginning, like co-inoculation, and each of these options have pros and cons, and I'll quickly point out some of them. If you are doing a co-inoculation, that means fermenting both together, conducting alcoholic malolactic fermentation together, is somewhat convenient, but it has a downside, and the downside is that sometimes the bacteria can overpower the yeast and start converting the sugar into acetic acid and thereby inhibiting the yeast growth. When that happens, you can end up with a sluggish or stuck fermentation with high VA, and that's not very desirable. On the flip side of that is you could wait till the end of alcoholic fermentation and then conduct malolactic fermentation. And in this situation, that some of the benefits include you have no SO2 because it's been bound, sugar is not a limiting factor, and yeast growth is not a issue because the growth has already occurred. But the downside of that is sometimes your alcohol content can be very high, and that can create problem in starting the malolactic fermentation. The medium can be depleted with nutrients, and that can also cause some problems. But most importantly is if you are doing post-alcoholic fermentation and conducting MLF, then you have to leave the wine without protection from SO2, and that's a somewhat less desirable situation. So for this reason, you should monitor the yeast alcoholic fermentation, and as soon as that's over, you can initiate malolactic fermentation. However, there is a compromise that's in between, a middle of the road approach that you can take, where you can initiate alcoholic fermentation, and then after a day or two, inoculate the must with lactic acid bacteria, and that will help you conduct both the alcoholic and malolactic fermentation. The one point that is important to remember if you are following this approach is that you want to be sure that the strain of yeast that you are using and the strain of bacteria you are using are very compatible. You want two friendly organisms to work on that, because if they are not friendly, you can end up with a problem in fermentation. So that's the three approaches, and I think if you are consulting with your supplier, they can give you a better recommendation on the strains to be used. The next point I would like to point out is that when you are conducting malolactic fermentation, the nutrition of the medium is very important. Because the bacteria are not capable of manufacturing their own food, so you have to provide through the medium. If you are conducting a red wine fermentation with skins or white wine surly aging, in those situations, the skin and the yeast autolysis process contribute more nutrient. But if you don't have that situation, you want to be sure that there's enough nutrients in the medium, and if you don't have, you should get a commercial preparation of the nutrient specially designed for the growth of lactic acid bacteria. Don't count on diammonium phosphate, it doesn't work. So just get the right kind of nutrition to conduct the MLF. The next thing I want to talk about is consider some of the factors that are responsible for inhibition of the malolactic fermentation. And then if you are going to encourage malolactic fermentation, you need to be aware of these factors. The first one is the pH. If the pH is too low, like below 3.2, the malolactic fermentation would be difficult to initiate. So you need to have a little bit 3.2 or higher pH to get started. Free SO2 will be another factor. Generally, if you are trying to do malolactic fermentation, you want less free SO2 in the medium. 20 ppm or less is a better idea. Anything more than that can delay or cause problem for the lactic acid bacteria. The third point I would like to mention is the temperature, and this is very critical because a lot of time you have temperature not very conducive, especially in the winter time, and then the fermentation is very difficult to initiate. So make sure you warm up your medium or the must so that you have at least 18 degrees C or more. Something like 20 to 22 degrees C is better. And when the fermentation temperature is good, the bacterial activity is also equally good. Lack of nutrients can cause inhibition. We already talked about that. But the other point I would like to mention is the competitive nature of the yeast. Sometimes yeast can take over, and then bacteria has difficulty growing. That's why it's better to do it after the yeast growth has happened, and then you can conduct malolactic fermentation. But just as long as you got compatible strains, you should have no problem. But the main problem we see in finishing malolactic fermentation after the alcoholic fermentation is the presence of high levels of ethanol. Around 12–13%, it becomes difficult, although I may point out that there are some strains these days available that would still conduct malolactic fermentation even if your alcohol level is high. So check those strains before you want to use them. One of the important points that needs to be mentioned here is that some people would produce sweet wines by adding potassium sorbate and hold the wine in bulk with the sorbate addition. And this is a riskier proposition because if you are holding the wine with sorbate in it, and if the wine gets contaminated by lactic acid bacteria, it can use the sorbate and produce a compound that gives geranium taint, and that is very difficult to get rid of it. So don't try to sweeten the wine, put sorbate and hold it off. Do everything just before bottling so that there is no chance of contamination. The next point that I would like to address is the issue of microbial stability post-malolactic fermentation. It is usually understood that once the malolactic fermentation is over, the wine is pretty much stable in terms of microbial activity. But a caution, it is stable, but the stability is a relative thing. Especially under high pH condition, you do not want to leave the wine unattended because the spoilage causing bacteria also like high pH. So consider using things like lysozyme in that situation. And add sulfur dioxide based on pH as soon as the malolactic fermentation is over. Now, we covered some of the information on lactic acid bacteria for malolactic fermentation. Now, I would like to get your attention to the fact that we can also use yeast strains to reduce malic acid in fermentation and in wine. The two strains that are mentioned here in the slide is Lalvin 71B. This has the ability to degrade about 30% malic acid, and this Uaffirm SVG also has the ability to degrade malic acid up to 25%. And in many situations, you will notice that it is the combination of yeast and bacteria that is going to give you the best acid reduction in terms of malic acid. There is a third option, and that has to do with a wild yeast, which is usually a spoilage causing yeast, and it belongs to a different genera called Saccharomyces pombe. This yeast has the ability to degrade malic acid completely But the byproduct of this degradation is the ethanol, so there is a greater reduction of acidity if you use this yeast strain. The problem with this yeast strain is it also produces higher levels of ethyl acetate, and that is a spoilage component in wine, and we don't want that in wine. So the Lallemand company introduced this new yeast called Pro-Malic, which is a Schizosaccharomyces pombe, which is encapsulated in an alginate. So you can introduce this yeast strain to conduct primary fermentation or alcoholic fermentation. Usually it comes in a tea bag format where you put this tea bag with this yeast in the must and monitor the malic acid content of the must. And when you reach to a desirable level of malic acid, then you can take the yeast strain out and then reintroduce with the desired strain of Saccharomyces cerevisiae to finish the fermentation. This has been tried a couple of times in our labs. It seems to do well with the white wine, but with the red wine, the skin and seeds is a little bit problematic. I'm hoping that at some point in time we can come up with a hybrid where some of these genes responsible for malic acid can be introduced in Saccharomyces cerevisiae that can conduct mellow-ethanolic fermentation and take care of the excess malic acid, which is one of the bigger problems with cold climate grapes. So with that, I think I will end here, and I would like to ask Katharine now to talk about the chemical.
Thanks, Murli. So if you would rather be a mad chemist than a mad microbiologist, the other option that we have for deacidification is chemical deacidification, and that's often useful in cases when you don't want to use malolactic fermentation. In chemical deacidification, we exploit the fact that when we add acids and bases together, we form insoluble salts, and by nature, insoluble salts are going to fall out of your wine solution and can be removed from the wine. So you can see examples of that on the right here in an old busted apart barrel, or on the wine cork in the left, the wine diamonds or potassium bitartrate crystals. So generally the salt that we're trying to form is potassium bitartrate, and a review of juice chemistry. We know that juice is supersaturated with potassium. We talked about all the ways potassium can get into the juice earlier, and when that potassium combines with the tartaric acid that's in the grape, we get potassium bitartrate, which is a salt. And the solubility for potassium bitartrate is very high in water but decreases in alcohol. So as we move from an aqueous-based juice solution to the hydroalcoholic solution of wine, our solubility starts to decrease and we get a greater potential for precipitation from solution. It also decreases with cooler temperatures and decreases around pH 3.6. So generally we want to cold stabilize to prevent crystal formation. When unstable wine is chilled, put the bottle of wine in the fridge and you get crystal formation whether you want it there or not. But even more helpful for us is the acid reduction that comes along with this cold stabilization. So in order to achieve cold stabilization or tartrate stability, we generally chill with or without seeding, and seeding is simply when you would add some potassium bitartrate early to the wine so that there's a place for crystals to start forming. You also can achieve it through ion exchange, although that is a much more expensive and difficult path for a smaller producer, or a combination of the above. And if you choose to go the first route, to chill your wine, you usually take about 2 weeks, chill the wine to 25 to 30 degrees Fahrenheit. You get your most rapid precipitation in the first 12 days, so leaving it in for the rest of the 14 tends to be enough to take care of everything. And the rate at which you'll achieve stability and get your potassium bitartrate to drop out of solution depends on, it varies by the type of wine, again because of matrix interaction. So a white wine is a simpler matrix than a red wine, so it's going to you'll achieve stability and get your precipitation complete faster. And your table wine is going to precipitate more quickly than dessert wine, because the sugars in desserts and sweet wines tend to bind up some of those or slow down the reaction so that it's not released from solution as quickly. One thing to remember is that pH bears on the type of TA and pH changes that you get when you cold stabilize your wines as well. And the reason for this is that potassium bitartrate is amphoteric, and amphoteric is a term that means it can act either like an acid, and it will when your pH is greater than 3.65, or like a base if your pH is less than 3.65. So when you remove your potassium bitartrate from solution, you're removing either something that's been acting like an acid or something that's been acting like a base, depending on what your starting pH is. So if you're starting with a wine with pH over 3.65, you're removing something that acts as an acid, and your pH is going to go up. Again, it tracks correctly. If your pH is less than 3.65, which is what most of us are dealing with, and we remove something that's acting like a base, our pH is going to go down. And generally, this isn't something that's a big concern. It only moves about 0.2 units, but it's a question that we often get as extension people, because people doubt their own measurements. So if you see a TA decrease but a pH decrease as well, that's why. It's nothing to worry about, just something to be expected. Now, the things that we can add in order to enhance the reduction in acidity that we get when we cold stabilize are carbonate compounds, and there are three primary ones that are traditionally used. The first is potassium bicarbonate, the second is potassium carbonate, and the third calcium carbonate, and we'll go through each of these in turn. But all three of them react with your tartaric acid. Murli mentioned earlier that tartaric acid tends to be stable and malic acid is not. Well, that's reversed when we're doing chemical reactions. Instead of affecting our malic acid, it pretty much stays as it is, and we pull out the tartaric acid. And the amount of tartaric acid you have in your wine is what's going to dictate the amount of acid you can remove with these chemical compounds. So adding more and more will only help you so much once you've exhausted the amount of tartaric that will react with it. The first of these compounds that I'd like to discuss in more detail is potassium bicarbonate, and it's pretty easy to use in my opinion. One, you can do a pretty good estimation of the type of acid drop you're going to get. If you add about 0.9 grams per liter of potassium bicarbonate, you're going to get about a 1 gram per liter drop in TA, so the math's pretty easy. Realize that this always varies by wine. It's just a rough estimate, but it's a nice number to bear in mind. Potassium bicarbonate precipitates only once, which is nice. You put it in, you stir it up really well, you give it a week or so. It's relatively fast, and if you chill in the process, you'll speed up this reaction nicely. So you certainly will have time to add a little bit of potassium bicarbonate, taste the wine again, decide if it's where you want it to be, and add a little bit more if you need to. So you can do some fine-tuned adjustments in this way. The downside is that it can only affect fairly small changes, and there are sometimes sensory effects. Some people are sensitive to sort of a chemical flavor or a solventy flavor, and you can also affect your the intensity of some of your fruit characteristics as you add this compound, more because you're changing your pH and your TA, but there will be some change in your flavor in some cases. Potassium carbonate was the second compound that I listed, and while it technically should act much faster or more efficiently than potassium carbonate, it's not one that we recommend for use in wineries, only because it's not very shelf stable. Unlike potassium bicarbonate, which if you keep it cool and dry will stay good on the shelf for a very long time, potassium carbonate is very hygroscopic, and so it starts to absorb water from the air as soon as you open it, and absorbs water very rapidly. The end game of that is that it no longer has any deacidification properties, so it's really better to stick with the potassium bicarbonate, which is marginally slower but much more effective overall. Our third choice is calcium carbonate, and calcium carbonate is something that we see people drawn to when they have very high acid wines, because an addition of about 1 gram per liter generally gives you, again, an estimated drop of about 1.5 grams per liter in TA. So it can be used to correct very high acidity, but its use is fairly limited. You can't use it towards the end of winemaking. It's something that really needs to be used in juice or must. It does tend to saturate your wine with a calcium salt, and calcium as a mineral is very bitter. Calcium carbonate itself itself has a chalking flavor, being as it is chalk, and it tends to precipitate over very long periods. My lab technician likes to call it the gift that keeps on giving, because you can put it in your wine, go through cold stabilization, get it in the bottle, and a year later you may have customers calling saying, you know, I suddenly have a bottle of wine that's snowing and I don't like this and I'd like to return it. So this is something that can be a cause of concern depending on the image that you are trying to project with your wines. One proposed method for overcoming this is the double salt method, the double salt addition that was developed in the turn of the last century and by a German researcher. And his theory was that under certain circumstances, calcium carbonate additions can be used to remove both tartaric and malic acids, and can be done in such a way that the calcium carbonate is completely consumed, so you don't have these instability problems later. And roughly what we do is pull out 1 to 5% of your juice, totally deacidify the tartaric acid. You then have adjusted the pH of that portion of the juice to about 5, which makes your malic acid much more able to interact with some of these other compounds and form salts. And then you return your neutralized juice to the tank, which, if all goes well, it's proposed will result in a chain reaction that removes both your tartaric and your malic acid. So the commercial information from the companies that currently promote this are as follows. You first have to measure your titratable acidity and your tartaric acid concentration. So right away we've got some information that's fairly specific that we need to learn about our wine in order to do this right. We remove 1 to 5% of the total juice volume. Add your calcium carbonate with constant stirring. And then make a second addition of tartaric acid and calcium carbonate, again with constant stirring. And I called some friends in Germany who still use this method, and they say, yeah, you pretty much just stir it until you quit seeing carbon dioxide bubbles coming up, and then you know you're done. So kind of a rough estimate, I guess, there. Then you filter the deacidified portion, return that to your tank, and then return the rest of your juice to the tank, again with stirring. You have to keep everything very well mixed up in order to have this reaction occur in a timely manner and give you the acid reduction that they propose. However, the claims for this method is that you'll get larger acid reductions, also that your calcium carbonate will be completely consumed and there'll be no lingering instability, that both tartaric and malic acid will be removed, and that your acid reduction will be due to the action of what's called a double salt, or a calcium tartromalate, which the hypothesized structure of which you can see over on the right-hand side there. And there are several problems with some of these claims that have been investigated over the years. So let's talk about some of those. Sorry, the question is, of course, can we use double salts on high malic wines? So the claims that one that we already know is not quite true is that as we have better and better ways to measure or identify crystals, we know that this proposed tartromalate does not form in this universe or any other as far as we know. So we aren't dealing with double salt. It's a misnomer. We're dealing actually with 2 individual salts that are occurring. So in order to investigate this issue, we started a project here at Cornell where we wanted to see if we made a model wine solution that acted like a wine that had a 1 to 2 ratio of tartaric to malic acid. What would happen if we could pull out more malic than tartaric? And so if you look at this first chart, this is a chart of some data that we gathered only from that first portion of juice. If you were doing this in a real wine situation where you would take out a portion of your juice and treat it and put it back into the larger bulk tank of juice, this is the data we got from that. So if you look, we started again with a 1 to 2 ratio of tartaric to malic acid. We did not stir this wine. After 8 hours, our acids leveled off, and you see that our tartaric acid is pretty much gone. We're almost to 0% acid remaining, and our malic acid is just under 40%. If you contrast that with this second chart, where we again had 1 to 2 tartaric to malic, but we stirred it the whole time. So you simulate this in a tank with a goose or something similar. you see that very quickly we remove all of our tartaric acid, and what's left is less than 20% malic acid. Now, there's two things to notice here. First is that you really do have to stir the whole time, not like stir it and walk away and come back and stir it. That's useful to know. The other thing that's interesting is that in both of these cases, we still have malic acid left. So that means that this portion that we're adding back to the juice in the tank has no tartaric but has some malic. Which we didn't expect. In theory, this should all be gone. And so what happens then when we add it back to the larger tank is that we've already got some malic in there. So the chance for, to simplify greatly, the chance for more malic acid reduction is not as great as the chance for more tartaric acid reduction. So from the data we have already, it looks like we may not be removing as much malic as we would like. One more slide that I want to show you here. In this case, we actually, in this chart, we're showing three different wines. The blue would be one that's 2-to-1 ratio of tartaric to malic. Red would be 1-to-1 tartaric and malic. And the green would be that 1-to-2 tartaric to malic that you saw in the last two slides. And this these bars just are the malic acid now, and what you see at the end of 8 hours is that the ratio of tartaric to malic in the starting model wine does not affect the amount of malic that we have left. So that's also interesting. We expected there would be a much bigger difference, and most of the literature hypothesizes that there is. So that might be good news for us if we have malic and tartaric and we need to deacidify, but it's still, we haven't answered all the questions yet, that's for sure. So we're continuing to work on this. There will be more data which we'll be publishing and also presenting for this project as we find it. But for now, what we know is that there is no double salt, that we're really dealing with two different salts, calcium tartrate and calcium malate. We also know that calcium malate forms very slowly. The kinetics of the reaction really favor calcium tartrate. So in order to get calcium tartrate to move out of the way and allow us to form calcium malate, you have to do some tricky pH manipulations that may or may not be possible in a real wine, even if we can manage to do it in a model wine solution. Also, we have learned that the tartaric and malic ratio doesn't influence the rate of deacidification. That's important to us. And that we still had residual calcium carbonate in our wine, and that again may be a problem. We may not be using all of that up as we think we are, so we're investigating that further. Also, total deacidification is impossible to determine, and we still don't know how much malic can be removed, although signs point to it not being a lot. How this reaction will change in various wines, because buffering capacity will change from wine to wine, and how much instability will remain from the unreacted calcium. So in summary, I think we've at least demonstrated that different types of acid, be it malic versus tartaric, will give you different pH and TA relationships, and we really want to push the relationship towards tartaric. That gives us a better pH-TA relationship. So ripen those grapes if you can. Also determine your wine style and type prior to making decisions. You may not have to deacidify at all. Maybe you can just add some sugar and balance the acid out that way. Your sensory impact is varied by acid content, and at this point malactic fermentation is the only way we know to preferentially remove malic acid other than those fairly experimental yeast that Murli was talking about. Further, if you do use calcium carbonate, you need to have some knowledge to do that. It has to be carefully managed, and you may or may not remove much malic. The instability is still a danger. So with that, I will turn it back over to Kristlyn.
Okay, everyone. So I went ahead and switched over to a different layout. This is our end layout. Go ahead and start typing your questions for Murli and Katharine. Two quick things. The Managing Acidity PDF is available there on the files too. And also we have a link to an exit survey that I would really appreciate if everyone fills out. So let's switch over to some questions. We have one that came in after the first part, and it reads, it appears that MLF is the best way to manage deacidification. Isn't there a risk of stripping some of the character or structure of white wines especially? A fair amount of malic acid can give the mid-palate a wow factor.
Murli, I'll leave that one to you since you were the malic acid presenter.
Okay, there's a question from Clyde. Hi, Clyde. You raised an important point, and that is, does the bound SO2 has a role in influencing the lactic acid bacteria? And the answer is yes. And not only free, but bound SO2 also can interfere with lactic acid bacteria. So you don't want bound or free SO2 if you are trying to do malolactic fermentation. Okay? Are there any other questions? I don't see.
Murli, I think the question was, is MLF the best way to manage acidity because that malic acid in the mid palate is desirable? Do you have feelings on that?
What was the question, Anna Katharine?
Is MLF the best way to manage deacidification? Can you risk stripping some of the character of white wines? And is malic acid useful in giving a mid palate a wow factor?
Well, first of all, it will strip some things, and that's why we suggest that any of these chemical treatment should be done on juice rather than wine, so that you have less danger of stripping out. But as far as the middle palate and malic acid, I think it's not as simple. It's got a lot more complex things going on with various components in white wine that contribute to the middle palate other than malic acid. Okay?
Chrislyn, do we have another question?
Okay, how about, is there a strain of NL bacteria that minimizes the negative aroma when used on white wine?
Yeah, the lactic acid bacteria can have an impact on aroma. Sometimes it can be positive, sometimes it can be well, negative in the sense it can suppress the fruity notes, or it can encourage fruity notes. Some of the work done by Thomas Hennickling at Cornell shows different results. So really we don't have a good handle on it, but I think if we are going to look at aromatic white wines like La Croissant, it may be a good idea to try different strains of lactic acid bacteria and look at the volatile aroma compounds and also sensory impact on the fruity notes of the wine. But in general, anytime you do malolactic fermentation, you are going to diminish the fruity component in white wine. So if you are focused on white aromatic wine production, then I would say don't bother with malolactic fermentation at all, and use chemical deacidification to lower the acidity instead.
Okay, I see that Ken Albert in Vermont asked if potassium bicarbonate is okay for use in very low pH wines. In low pH wines, it should be fine. I think the concern always when you're working with chemical deacidification is if you have a high pH wine, because that's when you run into the issue of you know, dropping acid and potentially raising your pH. So if you've got a low pH and a high TA, you've got plenty of room to work with. That's a good position to be in.
And I would further add that they should do a bench trial in your winery before you start treating the whole bulk tank, so that you have a better idea as to the extent the pH is going to be shifting upward when you treat the wine with potassium bicarbonate.
Yeah, I agree with that. That's something that we didn't really talk about in this talk, but any of these additions that you want to try, especially the chemical additions, doing a bench trial is always a great idea. You never can completely emulate what's happening in your tank, but trying to keep the conditions as much as possible similar to what's happening in your tank as far as temperature for storage and that sort of thing. It's the closest you can emulate and the more carefully you measure, the better sort of view into the future you're going to get with your bench trials. So learning to do those is a great idea.
Okay, Tim Martinson here. Can you all hear me? I think we're at about 1:15 now, so I think we're going to try and wrap things up. And we will be doing this again at 7 p.m. Eastern Time, 6 p.m. Central Time, for a different audience, hopefully. I'd like to thank you all for coming, and also stress that we'd like you to fill out the post-webinar exit survey. And please feel free to provide any comments about the presentation, about the way we managed the presentation. And we'd also like to get your suggestions on future topics we should cover in future webinars. And we will also leave the meeting pod open here after we've stopped talking for a couple hours, and you can certainly type in some more information and questions and comments on the chat line if you want to stay on for a little while. I'd like to thank Murli and Katharine for being the guinea pigs for this series, and I'd like to thank all of you for coming, and hopefully we'll be able to present these on a continuing basis and modify them as we go along based on your feedback. Hope to see many of you at the Minnesota Grape Growers Association Cold Climate Conference. So again, I'd like to close and thank you for coming, and we will send a follow-up email again with that survey link after the webinar is done, and also tell you when we've posted the link to the recorded version of this. Thanks for coming, and hopefully we'll see you next time. Bye-bye.
Thanks, everybody. Bye.
Bye.